Good morning. So today I'm going to talk about efficient data structures and algorithms for implementing lookup tables. So in particular, I'll be talking about binary search trees and how to prove in Coq that binary search trees have the properties you expect. And then I'll talk about how we formalize the organization of the properties we expect of an abstract data type in general. Some concrete data structure is meant to implement an abstract data type. What does that mean? And how do we prove it? I'll also talk about extraction of functional programs from Coq to ML so that we can compile them with an ML compiler and run them. Okay, so let's start with binary search trees. A binary search tree is a binary tree. That means each node has either, well, how do I say this? Binary tree is each node has no more than 2 children, but really each node will have exactly 2 children or no children. So this is a binary tree in the sense that the leaves that have no children are just not shown. And a search tree is one where at any node, the key value in that node is greater than the keys of all the nodes in the left subtree and less than the key values of all the nodes in the right subtree. And that means that searching for a particular key value in a binary search tree is reasonably efficient. If we're searching for, I don't know, 7, for example, we know that 7 is less than 8. So we know to go left. It can't be in the right-hand subtree. 7 is greater than 3, so we can go right. 7 is greater than 6, so we can go right, and we find 7. Or if we were searching for 5, we would find also in 4 comparisons that it's definitely not in the tree. It has to be in the subtree to the left of 6, in the left subtree of 6. It would have to be in the subtree that's the right subtree of 4. That's empty, so it can't be there. And if we're lucky enough that the tree is reasonably well balanced, then the height of the tree will be approximately log base 2 of the number of elements in the tree. And that means lookup or insert in a binary search tree will take log n time. Okay, so you knew all that, but now let's prove it. So we'll look at the search tree chapter of verified functional algorithms. Before I present is this font big enough to read in the back? Yeah. Yes? No? Yes. Yes, okay. I want to talk about a feature of Coq called sections that help organize sort of parameters to functions. So first let me do an example without sections. I'm going to implement a module for lookup tables implemented by association lists. So we're going to be able to look up natural numbers and get back values of some type V by walking down this list and finding the pair nat cross V where the nat matches our key and then returning V. So my map has to take a type parameter V that indicates what's the type of all the value elements. The empty map on type V is just nil. And remember, this nil has an implicit parameter that's the type of the values. So the implicit parameter here of this nil is nat cross v. Then the lookup function, this lookup function returns a value of type v. So we're implementing sort of a total function, lookup, and that means we need a default value to return in case the key is not in the association list. So lookup takes a v type parameter and a default value parameter of type v. There's our dependent types at work. And then finally we can take the key that we're looking up, the map we're looking in, and it returns a value of type v. And then we have a theorem, lookup empty, which says for all x, if we look up x in the empty map, we get the default value. So lookup empty also has to be parameterized by v and default. Here lookup is parameterized by v and default. Empty is parameterized by v. All these extra v and default parameters sort of get in the way of writing and reading this stuff. So let's do this again, but with the section command. We open a section called maps. We declare variable v and variable default. So v of type, default of type v. And now all of these definitions and theorems are implicitly parameterized by v and default as necessary. So when we write it, we just write my map without a v parameter, and we can refer to a v that's bound right here. And the lookup function, when it wants to return the default value, it just returns it. And if we check the type of lookup, well, let's define it first. All right, what's the type of lookup? It's nat arrow my map arrow v. Okay, so we prove our lookup empty function. We end the section. Now from outside of the section, we'll check the type of lookup, and it takes a v parameter, a default parameter of type v, and then the rest of the parameters. So now that the section is closed, we don't have variables v and default bound in the current context. They have become implicit parameters of all of these functions. Except notice that, I don't know, the type my map is type arrow type. This is v, but it doesn't have a default parameter. It didn't need it. So the section mechanism doesn't add it. If you want this to be added to every single thing in the section, whether it needs it or not, then I think you use the word context instead of the word variable. Okay, so that's convenient, except when it's not, meaning that you can overdo this section stuff, but we will define the program for binary search trees in a section with the v type. So our binary search trees will implement maps from the natural numbers to the v type, whatever v is, and we'll need a default value of type v to return when we look up something in the binary search tree and it's not there. So we'll have variable v and variable default of type v, just as we did for maps implemented with association lists. We'll define a key type that will be nat. And here's our inductive data type for binary search trees. The empty tree, E, is a tree. And the internal node, T, if you apply it to a left subtree, a key, a value, and a right subtree gives you a tree. So what could be simpler? Then we can define the interface functions, the operations on trees. The empty tree of type tree is just E. The lookup function takes a key and a tree, and, well, if T is empty, returns the default value. if T is an internal node with a left subtree, a key value, and a right subtree. If X is less than K, then just return the result of doing the lookup in the left subtree. And if K is less than X, then look up in the right subtree. And if neither of those is true, well, since this less than on the natural numbers is a total order, they must be equal. And we can return the value V that's bound to K right here. So there's lookup. Insert, well, we're doing pure functional programming here. So if you look in your algorithms textbook for insertion into a binary search tree, it says walk down to find the node with a null pointer and smash that null pointer with your new node. Okay, what do we do here? We walk down, and if X is less than the key value Y, then recursively insert X in the left subtree and then wrap a new tree node around the new left subtree and the old right subtree. Okay, so let's think about the time complexity and the space complexity of running these functions. Lookup takes time, well, proportional to the depth of the node in which you find your key. And most of the nodes are near the leaves. And so we can expect that lookup runs in time proportional to, in some sense, proportional to the height of the tree. Okay, that's the time complexity of lookup. What's the space complexity of lookup? Well, lookup doesn't cons any new nodes, so its space complexity is 0 or constant or whatever. What about insert? Well, again, the number of recursions in insert is proportional to the height of the data structure. How can we prove that? Well, because the word fixed point is used. Any structurally recursive function, right, can go no deeper than the height of the data structure. Okay? Of course, we can write a fixed point function that traverses every node in the data structure. So to prove that it's proportional to the height, we need to observe that there's only one recursive call in each branch of the if statement. Now, what can we prove about the running time of functions in Coq? Not too much formally in the logic, right? The proof theory of Coq doesn't give us a cost model for the execution of functions. And indeed, the logic is not constrained to execute functions call by value or in any particular order. These are mathematical functions. But if we are going to extract these functions to ML, to some call by value language, where we can tell something about the evaluation order, then we can reason informally about the runtime of these functions. Okay, what's the space complexity of insert if we're going to run this in ML, in some conventional call by value, garbage collected functional programming language? It seems like when we do insert, it builds log n new nodes, right? The number of conses is the number of t's that are applied in all the recursive calls all the way down. So the space cost seems like log n, and we compare this to the imperative function that walks down the tree and smashes one node in one place. And that seems like it has space cost constant per insert. But think about this insert function in the context of a larger garbage collected functional program. Either the surrounding program will keep hold of the old tree as well as the new tree, or it won't. The old tree will no longer be mentioned in any local variables. It won't be stored independently in any data structure. So in that case, the old tree can be garbage collected. We inserted one new node and copied log n old nodes. But then our copies are live. They're pointed to from whoever kept the result of the insert. And there are log n old nodes that nobody points to anymore. that can be garbage collected. So in that case, when the program doesn't need to keep an old copy of the tree, the space cost of insert is just constant, just like the imperative algorithm. And the time cost is log n, just like the imperative version. But what if the functional program keeps the old tree for some good reason? So now the insert space cost is log n. We have log n new nodes, and the old nodes can't be deallocated. So the space cost seems like log n when you want to keep a copy of the old tree. But consider the imperative program. How can the imperative program keep an old tree? Well, it could copy its tree. If it wants persistence in that sense, you can copy the tree. That's a linear cost, order n, to make a new copy of this tree so that now I can do a destructive update in the new tree. So when the imperative program wants persistence, it has to pay a substantial space cost. Okay, so the summary is the asymptotic time and space complexity of this program is just as good as the imperative programs, and perhaps better. The constant factors may be different, and you can measure that yourself. All right, let's define one more operation on search trees. I want a list of all of the key value pairs in the search tree. And this is useful in many cases for programs, for example, that want to iterate over all the keys in a tree, or they want to calculate all the values in the range of the tree. So here's a recursive function, elements, or elements prime is the recursive function that makes a list of all the elements in a tree. This one works quite efficiently because it works in linear time. For each node in the tree, it calculates the list of all the elements in the right subtree. It conses one node onto that list for the key at the root of the subtree, and then it calls itself recursively to cons on all of the elements in the left subtree. So this produces the elements in order. It's really useful that this elements function produces its list of key value pairs in sorted order by key. This makes things more convenient for many applications. And it's useful that this elements function works in linear time. So the interface function elements just calls the private function elements prime with the base value of nil, which is all of the elements to the right of the entire root. Okay, so what are the interface functions of binary search trees? Empty tree, lookup, insert, and elements. That's our data structure. Now let's prove some. Well, let's watch it in action. So let's insert the binding 4 bound to v5 for no very good reason in the empty tree, and then insert 2 bound to v2 and 5 bound to v5, and then we'll do eval compute in that, and we get this tree. So 4 is at the root, 2 is in the left child bound to v2, 5 is in the right child bound to v5. Now let's look up 5 in that tree, and we get v5. Let's look up 3 in that tree, and we get the default value. And let's calculate the elements of that tree, and we get this association list where 2, 4, 5 are listed in order. So that's a proof. What? Yeah, well, I inserted bound 4 to v5 inadvertently, so the algorithm is working correctly. Okay, so I've just given you a proof that this is correct, which would be good enough for most software engineers.